Hello and welcome back to more modeling with functions. This is part 2. We're going to look at some variation, proportionality. I know part 1 was just thrilling, and so you had to come back for part 2, that cliffhanger of the greatest integer function. Okay, but seriously, mathy. Definition. Let's let x and y denote two quantities. There's some quantities that are somehow related. Then y is directly proportional to x, or y varies directly with x if there exists a non-zero number k such that y equals kx. This number k is called the constant of proportionality or the constant of variation. I will most frequently use variation rather than proportion. Okay, so this is our whole formula. This is our go formula for this entire lecture. Let's see. Suppose a 15-pound weight stretches a spring 8 inches. Okay, we want to find the spring constant. So my input is the 15-pound weight. The 15-pound weight caused the spring to stretch. So 8 comes to me by the spring constant multiplied by 15. If I divide both sides by 15, we are going to get a horribly ugly decimal, but let's go with it. 0.5333333. Yeah, let's leave it as 8/15. So this is great. That's a spring constant. That tells us how strong a spring is. All right, the stronger the spring, the less it's going to actually stretch the spring overall. A higher weight, lower spring. Okay, moving on. But when I get a decimal like this, 0.5333333, I don't want to choose where to round that number, because as soon as I round it, I'm not using the exact number. I can mess up future results. So if I don't get a good decimal approximation, like a terminating decimal, I always use the fraction. Always. So if it's not a nice decimal, always use the fraction. Until the very last step, and then you can approximate. How far will a 25-pound weight stretch this spring? Well, I want to know the stretch of this specific spring that has a 25-pound weight. Remember, in order to multiply fractions, we'll multiply straight across, and 8 times 25 is 400. I know that because that's wrong. I know that it's 200 because 8 quarters is $2. 200 divided by 15, this is not going to be pretty. 200 divided by 15, we're going to have repeats again. But this one we kind of understand. And I'm going to put repeating. The 0.53333 is a little weird, but the 13.33, just threes, that's no problem. We know that's a third, right? The spring will stretch. That's 2 L's. 13 and 1/3 inches. 13 1/3 inches. That's how you would tell somebody. Would you tell them 13.3? As you're doing an experiment, yeah, that's probably what it would be. But 13 1/3 is the type of exactness we might use in language where maybe not in our calculations, and usually it's vice versa. Okay. What are we going to do when we're looking at variation problems? So when solving a variation problem, what did I do? I'm going to follow the steps. We're going to write the general equation for the type of variation problem that you were solving, and we're only going to work with direct variation in this video. We're going to substitute the given values in the equation, so the constant of variation k is the only unknown value, and solve for k. So when you're given information, your first step is always find the constant of variability. And then next, now use the k and find the requested quantity. So every time that we solve a variation problem, we're going to use these two steps. We're going to find the spring constant and then find the one that we want to know about. Here we go. Let y vary directly with x. So that tells us y equals kx. Find y when x equals 5. So this is what we want to find. If y equals 7 when x is 14. All right, so y is 7 when x is 14. Let's go ahead and underline that in green so we can see where it came from. 7/14, k is a half. And yeah, fraction would be great, but this is a terminating decimal, and I'm going to use a calculator. I'd rather use my k here. So now that I have my k value, I want to find y when, well, I know that my k is half and my x is 5. Well, what's half of 5? Half of 5 is 2.5. So y equals 2.5 when x equals 5. And that makes sense, right? Y is 7 when x is 14. It was cut in half. 5 cut in half, 2.5. Either one of these would be a fine answer. I don't need to circle them both. This green is not the answer. It's not the final answer. It's just step 1 in finding k so that we could use it to find the actual final answer. My goodness. All right. Now let's get into some physics here. I love physics. Physics, for me, physics is the most natural application of math. They should be married. Math cheats on physics with biology and chemistry and everything you could possibly from school, economy, all of it. All right, here we go. The table lists the force F needed to push cargo box weighing, I don't know where I was going with that, weighing X pounds on a wood floor. All right, so I have the force needed to push the box. So I have the box on top and I'm pushing against it on the bottom. We want to compute the ratio for each data pair in the table. Interpret your answers. Okay, so I want to do just ratios. I'm going to look at 150 over F over, read the problem, F divided by X. It gives us instructions. F divided by the X that got it there. F divided by the X that got it there. Force of 36 divided by 210, and force of 54 divided by 320. Let's pull up our calculator here. 26 divided by 150. All right. What's 31 divided by 180? Interesting. 36 divided by 210. I'm going to start writing these down. Our first one, it looks like, is 0.17 and then a whole bunch of 3's. Our second one is 0.1717. Oh my goodness. A whole bunch of 2's. The third one is 0.1714. Oh, this is a 0.17142857, and it repeats. I don't know why I put 2 5's. That should have been an 8. 5 7 1 4. Oh my goodness. Okay, yeah. So this part repeats, and that tells me that this simplifies to something over 7. That's it. That's actually 1/7. It tells this portion of it is 1/7 after I deal with some 0.17. Anyway, moving on. I had to write those down before I did this last one because I know it's going to go off the screen. Yeah, I'm a little less focused than usual in this video because I've just recorded 8 others, and I'm a little tired of recording. I'm going crazy. Okay, we have 54 over 320, we get 0.16875. So what is this? This means, if force is equal to some constant times x, then F over x must be our constant. Right? So what is this? If I was looking at this, it is a constant. Because this is pounds divided by pounds, the units cancel out. A constant of 0.173. A constant of 0.172. A constant of 0.171. A constant of 0.169. If I went 3 decimal places for each of these, I find that, hey, that 0.17 is pretty close to approximating this. And we can see that F over X, yeah, that makes sense, that that's going to be our ratio K. So approximate. The most carefully approximated I can get here is, I would say, K is approximately 0.17. That's fairly accurate. These three are all a little over 0.17, 0.169, or even 0.168725. That rounds to 0.17. That seems the most reasonable. Okay, so I want to graph the data and the equation together. And what would my equation be? My equation would be 0.17x. All right, so let's graph these together. In order to do so, we need to go to stats, and we're going to edit. My list 1 will be my x values, 150, 180, 210, and 320. And then I will list my y values. My y values, the force, 26, 31, 36, and 54. I make sure the lists are the same length. I cleared my screen just so I can focus on what I'm doing. I put that in my list so I can graph it. So let's graph these stat plots. Plot 1 is off. Let's turn that on. Stat plots, fantastic. I want my window, my x values should go from, let's go with 100 to 370. And let's go by 50. I don't know why 50, just because. The force that we have to apply, let's go from 0 to 75. And let's take that by 15s. So there's my data. All right, so at 210, we jumped all the way to 320. Yeah, that's a pretty big jump. All right, that makes sense. Now let's graph our function, our equation, 0.17x. And when we graph them together, we see that this is a really good fit to this line. So real life data gives us an approximation of an equation, and it's with this approximation we can estimate the force needed to push a 270-pound cargo box. Our force will be approximately 0.17 times 275. Come back to our calculator. 0.17 times 275, and we'll get 46.75 pounds, approximately. All right, we can estimate because with our real life data, we can find patterns that recognize, oh, hey, look, it looks like 0.17 is about the constant of variability or constant of proportionality. Remember, those two are interchangeable. So if I can approximate that, I can write an equation. If I can write an equation, I can make predictions of other things that might happen within this range. All right, so all of it comes together. Real world stuff, that's what you're in college for. That's, unless you're a mathematician, then I'll get to you. You're here to look at the world and figure out how to make it better, hopefully. And so we analyze. Pattern recognition is one of the most important things that you can have in mathematics anywhere. Approximating, being able to take those estimates, to interpret those answers, to see what they might be in order to formulate your equations. This is why we do math. And as you're a mathematician, this is it, because it just flows so nicely. All right, didn't mean to geek out with you on direct variability, but I did. And I hope you enjoyed this lecture. I will talk to you later.